students, I'm Dr. B. Ravi Kumar, Associate Professor, Department of ECE, Institute of Aeronautical Engineering. This is the last lecture, the discussion of tutorial question bank from Module 5, which is nothing but Sequential Circuit Fundamentals. So in this lecture, I'm going to give a simple explanation of how to give a significant answers for a given questions. And these questions taken from the question bank. Let us see that what are the most important, the relevant questions comes from this module 5 and how to give a significant answer for that. Let us see, basically in this module, the syllabus have basically covered with that the introduction about the sequential circuits and what are the different types of flip-flops. And once we know that all the flip-flops, then conversion between flip-flops, and then the example or applications of the flip-flop, make use of those flip-flops. We can create the shift register, we can create the counters, and finally that second part in the fifth module, we have counters, different types of counters and design of those counters, synchronous counter and asynchronous counters. So in that topics, we have studied about the design procedure for synchronous counter and design procedure for asynchronous counters. So let us see that the questions coming from those topics and how to solve and how to give the better answer for those things, those questions. Basically, if you see this question belongs to types of counters, and one of the counter which is nothing but synchronous counter. So this question basically designing of synchronous counter using JK flip-flop to count the following sequence 0 to 5, 6, 0. Again 0, it's repeat to 0 to 5, 6. So, and that undesired states are 1, 3, 4, 7 must go to 0 on the next clock pulse. This is basically one type of sequence. So in counters, there is a basic counters like binary counters or some ripple counters, and then we will see that ripple counter belongs to a synchronous counter, and I see that synchronous counters. So there are different types of synchronous counter. So any whether it is a synchronous counter or asynchronous counter, sometimes it is required to visiting of all states of a given sequence, or sometimes we require to visiting a certain states. So certain sequence in this, that is one of the example is that 0 to 5, 6. Again, once finish it of 6, it will go to 0. So rather than sequentially go to each and every state. So if you in this kind of problems, first of all we take that how many number of states are there and how many flip-flops are required to represent. Basically there are maximum is here it is 6 is the visiting states and 1, 3, 4, 7 is the not visiting states. So maximum is 0 to 7 means we require 3 flip-flops are enough to represent. So 3 flip-flops and 3 variables to represent each flip-flop. In that case, first we have to define that state diagram. So when we see this state diagram, so this is the I am representing, for the simplicity I am representing the decimal number only. Then we can represent with a 3-bit representation. If it is initially the state is in 0, then once applying the clock pulse, then it will move to the state 2. And once, for example, if it is a state 2, then it will move to state 5. And then if it is in state 5 is the present state, then after apply the clock pulse, it will move to state 6. Once finishing of state 6, it will go back to 0. These are the desired state diagram. And also there are some states which are there. If any state was there in that circuit diagram, then all those things must go to 0. For example, if you are in a state 3, we are in a state 1, state 1, state 3, state 4, state 7, all are undesired states directly go to 1. Whenever a situation, then giving that state is 1, 3, 4, 7, directly go to state 0. So once we preparing this one, then we can take the like an excitation table, like a table which having a present state and next state. So once we create this present state and next state, then we can take that. If it is, for example, present state is 0 0 0, next state is 0 1 0, present state is 0 1 0, next state is 101, present state is 101, next state is 110, present state is 110, next state goes to 0. And if the unused states also be mentioned in the table, 0 0 1 0 1 1 1 0 0 1 1 1. Also we can take that as same state, go to 0 0 state. So once we take this one, then we can create which type of flip-flops are required. If you use this JK flip-flop, J and K, so J, there are, so as I said, it requires 3 flip-flops. So 3 JK flip-flop, Z0, K0, J1, K1, J2, K2. So with the help of excitation table, we can make use of those, like what relevant inputs are required to J and K inputs to make that the flip flop changes to a next state by providing by with the from present state. What are the relevant inputs are required to provide, must be provided to the JK inputs to get the next state from the present state. So this is the I'm creating as one single row so that we can understand how to create this table. So for example, present state, we know that the excitation table for the JK flip-flop is, if present state is 0, next state 0, then what are the inputs must be connected to J and K is 0x. So like that we have a excitation table. So 0 0 0x, 0 1 1x, 1 0 x1, and 1 1 x0. Okay. X0. So if it is present state is in a, if you take that 3 variables, if it's a present state 0, the next state is, I am representing with variables ABC. That A is, take the compare with the A variable. Present state is 0, next state 0, then J0 is equal to 0x. Present state is 0, next state 1, like J1 K1 is 1x. Present state is 0, next state 0, like 0 and 0x. And present state 0, next state 1, like 1x in that table, 0 1 1x. And present state is 1, next state 0, x1. Present state 0, next state 1, 1x. So by creating this table like that, so I'm creating the first one is J0 K0 so that you will be understand this one. Then this 1 1 x0, 1 0 1 0 x1, 0 0 0x, 0 0 0x, 1 0 x1, 1 0 x1. So now I'm taking the Boolean function for this one, J0. Take the what are the required input for that J0. We can take that values 0 1 0 and 2 1. Next 5 6 don't care. I'm taking the 3 variable K0. Five 6 don't care. 2 5 6 2 1 5, 6 don't care, and 4, 7 don't care. 4, 7 don't care. So we have only, this is the only possibility to create pair. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. For this one, J0. J0 is equal to, we can connecting B into C bar. Like that. Once you know the Boolean function, you draw the logic diagram. So like that, we can take the Boolean function for K0, Boolean function for J1, K1, J2, K2. So what are the relevant inputs? We need to connect with the help of Boolean function. Then draw the logic diagram. Then the second way of question coming from this model is how do you convert JK flip-flop to D flip-flop? So we can replace with this question with any number of any conversion to any conversion. You can take JK to D flip-flop. You can take SR flip-flop. For example, I am taking this example like JK to SR flip-flop. If otherwise, if I am replaced with JK to SR, JK to D, JK to T flip-flop, whatever it is. So otherwise, we can take any flip-flop to any flip-flop. You have to follow the same steps. Okay, what are those steps? Let us take the steps involved from any conversion to any flip-flop to any flip-flop. So first step need to be do is write the truth table of a desired flip-flop. For example, my conversion is JK flip-flop to SR flip-flop. Conversion between JK flip-flop to SR flip-flop. Here it is given flip-flop. We need to, it is a desired flip-flop. It is given flip-flop. So what are the important steps to be followed in the examination before conversion of any flip-flop to any flip-flop? Check that who is the given flip-flop, who is the desired flip-flop. Let us consider this example. Let us convert a JK flip-flop into SR flip-flop. The desired flip-flop is SR, given flip-flop is JK. First step, write the truth table of a desired flip-flop. So here it is desired flip-flop is SR flip-flop. So what is the truth table for desired flip-flop? SR flip-flop. Then once you get that one, then obtain the excitation table for the given flip-flop. Here in this case is JK. In this case is SR flip-flop. Then once you get the truth table of a desired flip-flop, excitation table for a given flip-flop, then append the excitation table of the given flip-flop to the truth table of the desired flip-flop appropriately to obtain the conversion table. So from that conversion table, simplify the expression for the input of the given flip-flop. What inputs must be given to the J and K so that it will be converted to SR flip-flop. Let us see that first step, truth table of the SR flip-flop. We know that what is truth table. If the 0, 0 is not given unchanged, nothing but present state is 0, next state 0. And if 0, 1 is given, it is 1 comes under R. So it will become that whatever the present state output is, the next state is reset, nothing but 0. So irrespective of whether it is 0 or 1, the output is 0, nothing but it is reset, it is unchanged. So next 1, 0 is given, that whatever the input of 0, 1, the output is set, these two. So this 1, 1 is given invalid. This is the truth table for SR flip-flop. This truth table, take that for the desired flip-flop. Once again, for the second step, obtain the excitation table for the given flip-flop. Given flip-flop is here is JK flip-flop. So that JK flip-flop truth table it is. From this truth table, we can get that excitation table. What inputs of JK, what inputs must be given to JK to get the next state from the given state, from the present state. For example, I am giving J is equal to 0, K is equal to don't care means whatever it is K, I am getting next state is equal to 0. Okay, whatever from the present state. If present state 0, next state is 0. If J is equal to 1, k is equal to don't care. So my next state is 0 from the present state 1. So what are the necessary inputs are required to get the next state from a given present state? So like that, the 1 0 from present state to next state 0, then my inputs are must be x and 1. If present state 1, next state also must be 1, like 1, then my inputs must be x 0. So for 0 0 combination, present state 0, next state 0, then 0x, present state 0, next state 1, inputs are must be 1x, 1 0, x1, 1 1, x0. From this excitation table, we can take that into the adding appended with this excitation table of a given flip-flop to the truth table of a desired flip-flop to get the conversion table. In this case, it is a truth table of a desired flip-flop, excitation of JK flip-flop. When we join together, we will get. So in this case, so if present state 0, next state is also 0, then my JK inputs must be like JK is 0x. If 1 1, x is 0. Like that, we can adding of excitation table with this SR flip-flop truth table. From this, we can get the what input must be for J, getting from the Boolean expression for the K map. And by considering that J, S, R, like present state, these are the inputs in the K map. So by considering S and R, Qn, you will get the Qn plus 1 of JK. Okay, what must be inputs are required to provide to get the next state. So for the J, you will get this one K map by providing this column. What are the zeros, x, ones that provide in the K map? You will get the J is equal to S. So when J is equal to S means, so whatever that J, in order to convert that J to SR flip-flop, J input is connected to S input, and get this K input is connected to R input, so that you will get that final conversion of JK flip-flop is. So simply you can connect, take the JK flip-flop, we can directly connect the S input like S is equal S R. You can connect J here, you can connect K. You will get the SR flip-flop. So J is connected to S and K is connected to R. You will get the conversion between JK and SR flip-flop. So like that, you can convert any flip-flop to any flip-flop by following those steps. Next, we will see that another important question from this module. Explain the design procedure of synchronous sequential circuit with an example. So if any synchronous sequential circuit can take that conversion, like the states are simply counting up counter, simply down counter, simply a counting of a sequence using synchronous sequential circuit. Okay. So basically, synchronous sequential circuits are, if you take any 4 flip-flops, all 4 flip-flops are parallelly connected with a single clock. This is called this nothing but synchronous sequential circuit. So based on the requirements, we can get that steps. Then we can design the synchronous sequential circuit. So the design steps in this means, first you have to see that number of flip-flops are required. How many number of flip-flops are required need to be considered. Find out number of flip-flops and the states. Then once you know the number of states and flip-flops, then we can create a state diagram. From that state diagram, we can make state table. In the state table, it is a table relationship between present state, next state, and then inputs of the desired, like inputs of flip-flop. whatever flip-flops we used to design the sequential circuits. Then Boolean function. What are the combination circuits are connected to that flip-flop inputs, we will get the Boolean function. Then draw the synchronous sequential circuit. These are the steps. These are the I'm giving a short form of the steps to get the synchronous sequential circuit. So in this basically, if you see this one, counters are the most important examples of sequential circuits. Basically, there are two types of counters. Asynchronous counters, which is also called ripple counter. Ripple counter is a counter. The output of the one flip-flop is driven to the other flip-flop to get changes of the states. Only the first flip-flop is driven by the main clock. The remaining flip-flop states are changes by driving the output of the previous flip-flop. That is rippled by the previous flip-flop. That's why they are called a ripple counter. And we can create a up counter, we can create down counter, we can create a up and a down counter using this one. Then we have a synchronous counter. Also called parallel counter. It requires only single clock to drive all the flip-flops. And then shift register counters. Shift register based counters, using the formation of shift registers, just we can connect that output of the last flip-flop is connected back to the input of the first flip-flop. You will based on that in a manner to connect the first flip-flop output is uncomplemented output is connected back to the input as a ring. Then this is called a ring counter. Also called circular counter. Second type of counter is called Johnson counter. Also called twisted ring counter. Such twisted counter. So this one is simple connection. Take the flip-flop. The output of the first flip-flop is connected back to the input of the output of the last flip-flop is connected back to the input of the first flip-flop. Suppose if you connect a complement of the last flip-flop, Q bar is connected back to the input of the flip-flop, then it is called Johnson or twisted ring counter. So based we can simply connect those shift registers of the flip-flop, then connected in a manner that the output is connected back to the input and the complement output is connected back in first flip-flop. Based on that, we can divide into ring and twisted and Johnson counter or twisted counters. So they will also ask that explain the operation of ring counter, Johnson counter, or some synchronous counters, or some asynchronous counters, so that we can create any counters. So, and also one more example for this one is modulus counter, like mod counters. Based on the states are required. For example, if I want to repeat a sequence like 0, 1, 2, 3, 4, 5, 6, 7, again 0, then we use the mod 8 counter. So based on the modulus 8 number, that numbers can be counted by the counter and then repeat go back to the initial and then it will repeat the same count. So this way we will get that questions from this module, fifth module. And we can get this information from this digital design by Mavis Mano and the question bank from IARE website. We will go through that one. You will see the many number of questions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.